I'm going to give a very brief introduction to electrochemistry. I'm going to focus on the galvanic or voltaic cells, as they're both called, and then the next video will focus on electrolysis. So in order to be somewhat successful at your electrochemistry, you have to be able to assign oxidation states. This is a way of keeping track of electrons. You had this information way back in chapter 4, but you've probably long since forgotten. This isn't really true of what is actually happening with those electrons, but it is a way of keeping track of those electrons as they are gained and lost. It's a bookkeeping method. Many reactions do not fully, even in ionic bonding, do not fully transfer their electrons. So the rules for assigning oxidation states are pretty simple. If it's an element, you give it an oxidation state of 0. If it's a monoatomic ion, it's usually equal to the charge of that ion, like group 1 has a +1 and so on. Oxygen is the oxide ion, is given a -2 always, except in the peroxide ion, where it is given a -1. Hydrogen in covalent compounds is a +1. There are a few compounds where hydrogen is given a negative charge, as in a sodium halide, but for the most part, we're talking about covalent compounds. Fluorine, your highly electronegative element, is given a -1 in the compounds. And then your oxidation states have to add up to a 0 in a neutral compound and the charge of the ion if it is a charged species. So we will practice on assigning those oxidation states. Again, 0 for elements. Here you can tell. So you've always figured out oxidation states. When you named this iron 3 oxide, you knew what charge it had. Neutral atoms have a 0. And of course, that's aluminum with the +3 and the oxide ion with the -2. So redox reactions are oxidation and reduction reactions. They have to occur together. One species loses electrons and the other gains those electrons. So we're transferring electrons. A loss of electrons is called oxidation. So you have a more positive oxidation state after you have lost your negative electrons. Reduction is a gain of electrons. So if you're gaining that negative charge, you're going to become more negative. A good mnemonic to keep this straight is oil rig. Oxidation is loss. Reduction is gain of electrons. Originally, oxidation was defined as reacting with oxygen. So in this example, iron is indeed oxidized to iron 3 oxide. So it did react with the elemental oxygen to form the oxide. So it still fits the criteria for oxidation, and it still fits the basic idea that you have become more positive with your oxidation state. You've got a +3 oxidation state on iron as an ion and a 0 for iron as a metal. Half reactions take the oxidation and reduction half reactions and separate them. So iron has gone to iron 3+. It has lost electrons. It became more positively charged. All of those fit the definition of oxidation. When a free metal forms a compound, when a free metal forms a compound, any compound, does not have to be an oxide, it has been oxidized because it will be forming a cation, a positively charged metal ion. Its oxidation state becomes more positive. So potassium has been oxidized from 0 to +1. Again, you do not need to react with oxygen to be oxidized, but if you do, you certainly are oxidized as well. But the general definition is that you form a positive cation in the formation of a compound. If iron was oxidized, then something had to be reduced. Okay? So oxygen as O2, when it enters into a compound, will always be reduced. It starts out as a zero and its charge becomes more negative. That's a reduction in the charge. That's called reduced. Oxygen has gained electrons. So if iron's giving up those electrons, something has to take them. So if iron is oxidized, then oxygen takes those electrons and is reduced. In being reduced, it acquires a more negative charge. Reduction is the gain of electrons. If oxygen, diatomic O2, is a reactant, it will always be reduced during the reaction. It will always be forming an oxide. Reduction was originally defined as the removal of oxygen from a compound. So iron and oxygen will transfer electrons so that the iron acquires a more positive state by losing electrons, and oxygen gains electrons. Of course, we would have to balance those electrons. Okay? Iron is losing 3 and oxygen is gaining 2, so we'll balance those. The oxidation state is increasing or becoming more positive. The oxidation state is reduced, indicating reduction. So you just need to keep track of one process. Some people keep track of the reduction by looking at the reduction in charge. Some people look at the oxidation of a metal as it forms a compound. So whatever is happening to one species is the opposite of the other. All single replacement reactions are redox. You recognize a redox very clearly by a zero charge for a metal forming an ion. So all of these metals were oxidized and all of these nonmetals were reduced. Now you can also have metal-metal reactions where one metal is more reactive than the other. So it will undergo oxidation while the least reactive metal will undergo reduction. In all single replacement reactions, the most typical, you've got a metal and an acid and a metal and an ionic compound. So your hydrogen is going to be reduced to H2 gas, and one of your metals will be oxidized and one of them will be reduced. Your least reactive metal will be reduced. So when you're writing your half reactions, you simply want to lose and keep track of those electrons as they are gained and lost. So as sodium forms the sodium plus 1 ion, it loses an electron. Electron is on the right-hand side as a product. As chlorine is reduced, so sodium is oxidized, and chlorine gains electrons and is reduced. Zinc is oxidized. Hydrogen is reduced. Both of these transferred equal numbers of electrons. Zinc is oxidized. Copper is reduced. Again, an equal number of electrons are transferred. If you do not have an equal number, you will have to balance that half reaction and balance out those electrons. Copper is oxidized and silver is reduced. So you would have to make sure that you multiplied the silver to get those 2 electrons, to cancel out the electrons. The electrons lost by one reaction are gained by the other. So what we're interested in this short video is the use of chemical energy becoming electrical. In our next video, we'll look at electrical energy becoming chemical. But we're interested in the formation of a battery. We call these batteries galvanic or voltaic cells. Both terms are the same thing. They're a chemical reaction that produces electricity. So if you did a single replacement reaction in a single container, you would get zinc forming zinc 2 plus. So your zinc would dissolve into the solution and your copper would plate out, and the reaction would happen in one container. So your electrons are being transferred, but you're not getting any useful electrical current. You're losing most of that electrical energy as heat. You need to be able to separate the oxidizing and reducing agents so that the electricity, the electrons, have to flow from one compartment to another, and you can capture them and use them. So if we separate the reduction and oxidation reactions and make those electrons transfer through a wire, then we can use them. They can be used to light a light bulb or run a toy, or recharge your electrical appliances. Of course, it'd be hard to recharge much with these batteries since they don't produce much voltage, but you can use that electricity traveling electrons. So electrons are going to travel through the wire to get from the more reactive metal to the least reactive metal. So you're going to place your metal in its own ion solution and the other metal in its own ion solution. You're going to have a connection called a salt bridge that allows for ion travel, and then wire that allows for electron travel. If you do not have the salt bridge, you cannot maintain electrical neutrality, and you will build up opposite charges, and you'll have too much resistance to the flow of electrons. So let's look at a simple copper-zinc battery. So here's a zinc sulfate solution and the electrode of zinc metal, and a copper sulfate solution and copper metal. This is a porous barrier. So sometimes instead of a salt bridge, you have a porous barrier that allows ions to travel directly. So the net ionic equation is that zinc is oxidized, so it is losing electrons. The more reactive metal will always lose the electrons. Okay? The copper ions in solution are gaining those electrons and plating out on the surface of the electrode. So this electrode is forming more ions, while this electron is gaining more metal. So your half reaction for zinc and your half reaction for copper. Nice example cell because the electron transfer is equal. You have to connect the two metal electrodes with a wire. So the electrons will travel from the more reactive metal in order to move over, to reduce the least reactive. So the electrons will travel in this direction. The direction that they travel in is from the anode, which is your more reactive metal, to your cathode, which is your least reactive metal. The anode and cathode are the actual metal electrodes. So oxidation always occurs at the anode, and reduction occurs at the cathode. In order to keep electrical neutrality, so if you are losing electrons over here, okay, then you are becoming positively charged over here. And if you're gaining electrons over here, you're getting a net negative. So your ions are going to travel through the porous barrier to balance that. So your positive cation will travel over to the cathode side, and your negative anode will come over to the anode. So that's pretty easy to remember. Cations flow to the cathode and anions flow to the anode. And the reason for this is to create electrical neutrality within the cell. So once you get these electrons traveling, again, you can use and capture those electrons as electricity. So at the anode, the solid zinc is losing its electrons, and they are becoming zinc ions and becoming aqueous solution. So the anode is getting smaller as the zinc metal forms ions. The opposite is happening to the cathode. As the cathode gains those electrons, so those electrons come down, okay, and they're going to take the copper 2 plus ions, gain those 2 electrons to plate out copper metal on the copper electrode. So the copper electrode is going to get larger as the zinc anode gets smaller. Now that you know the direction of that flow, you want to be able to figure out the voltage of the cell. This is called the cell potential. And this little zero, just as it always has, stands for standard states. And for electrochemistry, that's 25 degrees, 1 atmosphere of pressure, and a 1 molar solution. We call this the electromotive force or the cell potential. And that's the symbol for electromotive force or cell potential. So we know that we're going to have electrons going from high potential energy down to low. That's just the natural tendency for all substances. And if you think about your thermodynamics, which is the driving force of everything, electrochemistry is a part of that thermodynamics, which is why it's often included with it, because you are creating high potential energy down to low potential energy. So electrons are going to flow, only in one direction. The greater the potential difference between the anode and the cathode, the greater the cell voltage. So when you have a copper zinc battery, the difference between those potentials is 1.10 volts. If you pick a larger difference, like a zinc silver battery, then you will have greater cell voltage. So you will be given all of the cell voltage and reduction reactions that you need on the exam. You used to be given the entire table, but now you're only going to be given the parts that you need. And all of these are written as half reactions, and they're all written as reductions, as if they were gaining electrons. That's just the way that the information is provided. Just like anything in chemistry, when you're provided with that value, you have to interpret it. So everything is compared to hydrogen. Elements are either easier or harder to reduce than hydrogen. This is nothing more than a fancy activity series. So here's your hydrogen potential right in the center, and it is given a 0 value. So you are looking at things that are more reactive than hydrogen down here and less reactive than hydrogen up here. Kind of backwards from your activity series. So hydrogen is assigned a reduction potential of 0. And notice you have some negative cell potentials and some positive cell potentials. So what does that mean? The more negative the cell potential, the more negative that voltage for a half reaction, the greater the tendency for that reaction to occur in the direction opposite of that at which it is written. So remember, they're all written as reductions. So if that value is more negative, then we're saying that that reaction tends to want to occur as an oxidation. The more positive that value is, okay, for the half reaction, the greater the tendency for that reaction to occur as it is written. So it wants to occur as a reduction. So let's look at an example. So here's your hydrogen in the center, and here's your magnesium, and it's written as a reduction, the ion gaining electrons to form the metal. And up here, we have fluorine written as a reduction, F2 gaining electrons to form the fluoride ion. If you were looking at comparing magnesium and hydrogen, magnesium with its more negative value, we're saying magnesium doesn't tend to want to undergo this reaction. It wants to tend to lose its electrons. It is a reactive metal, and it wants to tend to lose those electrons, in the reaction. Your nonmetal elements, of course, want to gain them. So you can see that fluorine would want to have a reaction where it is gaining electrons. If you were comparing magnesium and aluminum, aluminum is has far less of an ability to lose its lose its electrons and wants to undergo a reduction. Since magnesium is a more reactive metal than aluminum, it has a more negative cell potential, and of course we're going to want to fix that when we come up with the entire voltage of the battery. So reactions that are more easily reduced will gain electrons. Reactions that are difficult to reduce would rather lose electrons. Lithium, extremely reactive metal, would prefer to do the reverse of this reaction. So how are we going to get the entire battery voltage? Since all reactions are written as reductions, we're going to have to reverse one of our reactions. We're going to have to reverse our oxidation. So if we have a reaction that is given to us as a reduction and we need to reverse it, we simply change the sign of the voltage. So the entire battery, the cell voltage, will be the voltage or the potential of the reduction reaction plus the oxidation reaction. But a spontaneous cell, and again, here's your good old spontaneity from thermodynamics, always has a positive cell voltage. So and all batteries are going to run in the direction where they are spontaneous. Okay? If you hook up two different metals in their solutions, electrons will flow from one to the other. They will flow from the more reactive metal to the less reactive metal. They will always run to get a positive cell voltage. In order to get a positive cell voltage, you're going to have to reverse the most negative value. What you're doing is flipping that reaction. If all of those reactions are written as reductions, and a battery depends on you having a reduction and an oxidation, then you have to determine which reaction is going to run as an oxidation, and you're going to flip that one. The one that you're going to flip is the most negative value because that's the one that tends to run in the opposite direction. So you could have two positive values. One of them is still going to have a greater tendency to want to lose its electrons. So anything that's going to be oxidized is going to be reduced. Okay, excuse me, it's going to be reversed. So you want to get the most positive cell voltage that you can get in your battery. So you're always going to change the sign of the oxidation reaction. And then you're going to add it to the reduction reaction. So let's look at this reaction. Here's a net ionic equation of what we would call a copper iron battery. So in order for this battery to run, we've got copper electrode in copper ions, and your iron, okay, and we'll look at these later, we've got iron being reduced from iron 3 plus to iron 2 plus, so it's not going all the way to a metal. When you have some of your transition metals, they can often just be reduced to a lower charge rather than all the way to the neutral metal. So if we were to look up on our reduction potential chart, we would see iron 3 plus gaining an electron going to iron 2 plus would give us this voltage, and copper 2 plus gaining 2 electrons to form copper solid would give us this. Both reactions written as reductions, but one of these reactions has to be reversed. So if you look up at this equation, you can see that copper is the substance that has undergone oxidation, while iron has been reduced. So if copper has undergone oxidation, then we need to flip, okay, the reaction of copper. So we can look up there. Even if we did not have this, we could easily see that while both of these values are positive, this is the least positive value. So we have to add these two values together, but we have to flip one of them. So we need to flip the one that is the most negative or least positive to get the greatest cell potential. So we flip this one because that is what the chemistry is. You can see that copper has been oxidized. Okay? And then we add them together. If we had flipped the other one, we would have less cell voltage. You do not ever need to multiply your cell voltage by any coefficients or numbers of electrons in order to get your cell voltage. This is a property that does not depend on the number of electrons. That cell voltage doesn't matter. You can have a very small amount or a large amount, just like density. You can have a large sample or a small sample. The density is the same. The cell voltage is the same. So in order to describe our galvanic or voltaic cell, we have to be able to balance a redox equation, label the anode and cathode. The anode is always the more reactive metal. You have to know where the oxidation is occurring, and oxidation always occurs at the anode. You have to show the direction of electron flow, and electrons always flow from the anode to the cathode. The ion flow through the salt bridge or through the porous barrier. So your anions flow to your anode and your cations flow to your cathode. And then you have to calculate the cell voltage. So here is a balanced net ionic equation. Okay. Here is the calculation of that cell voltage. So if you look, zinc is the more reactive metal, so it has been oxidized. So in order to get this voltage, okay, we have to reverse the oxidation reaction. So we changed our sign of our zinc. We've got our electrons flowing from cathode to anode. Oxidation occurring here, reduction occurring here. This electrode is getting smaller and turning into ions. This electrode is getting larger as metal plates out on the surface. So the reason we know that we have to flip this reaction is if we look at the balanced equation, and they may or may not give you the balanced equation, but they're certainly going to tell you that you have iron and silver, and they're going to give you access to the redox potentials. So iron is more reactive than silver, and iron has been oxidized and silver has been reduced. If iron has been oxidized, then we're going to take its reaction that's been written as a reduction and we're going to flip it so that it is going in the correct direction, so that we want iron to turn into iron 2 plus, okay, and silver to be reduced. And then we're going to get our cell voltage. So a very simple math to figure out this cell voltage. They can give some more challenging ones, but once you learn the basics, you can find the voltage of any combination of metal and metal ions.